Question 2 on heat is the barbecue design. We've got Todd putting 0.050 kilograms of oil onto the hot aluminium plate. The initial temperature of the oil is 15 degrees Celsius and it heats up to 250 degrees Celsius. The energy absorbed by the oil to reach this temperature is 23.2 kilojoules. A. Calculate the specific heat capacity of the oil. Now this is a mathematical question, a few little tricks, but we pretty much just use this formula. Q equals MC, change in temperature, where Q is the energy you've put in, M is the mass, C is the specific heat capacity that we're trying to find out, and delta T is the change in temperature. So we'll rearrange this to find C, because we're after C. C equals Q divided by M, change in temperature. Q is this, M is this, and the only trick here is the change in temperature is 250 minus 15, which is 235 degrees. So we substitute all of those numbers in and we get a specific heat capacity of 1974 units are joules per kilogram. The negative one is per degrees Celsius. Okay, B. The diagram below shows the structure. Oh, I'll just go back up. One little trick up here. Don't forget that this is given in kilojoules. The K means times 1,000, so you have to be aware of that. So B. The diagram below shows the structure of the barbecue. Some of the main heat efficiency features of the barbecue are the burner box cover. We should look at these things as we're going. So there's the burner box. Oops, I'm using the wrong thing. That's the burner box cover. The shiny steel hood, which is up the top here, and the wooden stand. Okay, so they're pointing out these features out of all of those features because we're going to have to use them later. Use your knowledge of the heat transfer to explain how any of the two, we're going to use all three, of the three features mentioned above help the efficient heating of the barbecue. So, there are three kind of things to consider with this, is conduction, convection, and radiation, and perhaps combinations of these, and we need to consider how each of these three things use conduction, convection or radiation to help make efficient heating. Okay, so I'll just I'll talk about them and all the right stuff. The wooden frame, it's a good start. The wood is a very good insulator, good heat insulator, so it stops the conduction of heat away. So we'd say the wood insulates the heat, stopping heat loss due to conduction. Okay, I won't write them all out in full, but this just gives a model of it. So you've stated the part, what it does, and which of the energy loss things it's helping. That's just a good structure for it. Let's talk about the shiny steel hood now. The hood will trap any air and minimises the amount of heat lost by convection. So it's convection. With the hood, the steel burner, excuse me, burner cover. That's, you can see you've got the flames under here, and the burner cover would go all the way across usually. This is just a cutaway so you can see what's in the diagram, and that's doing two things actually. It's stopping air coming in and heat loss through convection, but also stops radiation, because it's going to, any radiated heat is going to be absorbed by it and transferred to the aluminium hot plate above by conduction. You could talk about a little bit about the shiny steel hood, but being a radiation reflector, but it's actually on the underside that we're interested in. to preserve efficient heating. So that's usually the underside is covered in grease and muck, so unless it's very, very clean. So that's not something that's a huge consideration. Moving on, the aluminium hot plate on the barbecue has a mass of 1.65 kilograms. Its initial temperature is 20 degrees, and after heating the temperature reaches 300. The specific heat capacity of aluminium is 897 joules per kilogram per degree Celsius, and the power provided by the gas flame is 1.38 kilowatts. Calculate the minimum time, okay, we're after the time, that it would take for the aluminium hot plate to reach the correct temperature. Okay, so the time part of it is going to come in with this equation. Power is energy over time. We've got the power, and we are trying to find the time. So time is our question mark, and we can work out the energy, which is going to be Q, from this equation, MC, change in temperature. So Q is the energy that's been contributed to the heating process. So we're going to run the numbers for that. We've got the mass, 1.65 kilograms. We've got the specific heat capacity, 897 joules per kilogram per degree Celsius, and the change in temperature is 20 degrees to 300 degrees, which will give us 280 degree Celsius change. So we plug those numbers in to find Q, which is going to be around about 400,000 joules of energy, and then we have to put that 400,000 joules of energy in as E and rearrange. So we'll have T equals E over P, and in this case E was our approximate 400, that's actually 414,414, and we're going to divide that by the power, which was 1.38 kilowatts. Remember, kilowatts is times 10 to the times 10 to the 3, which is 1,000 times, so that's going to be 1,380 is what we plug in place of the power. And when we calculate that out, we end up with around about 300 seconds, which is about 65 minutes. Okay. D. Explain why in reality the aluminium hot plate would take longer than this to heat up to 300 degrees Celsius. Oh, okay. Well, the big idea here is that it's not 100% efficient. So we're going to explain that further. Not 100% efficient, and what that means is that the energy is not perfectly transferred. There will be heat loss to the surroundings. Let's see, you would have conduction, because we need to get specific here. So you could have conduction heat which transfers to the air, which then convects away. So if you put your hand over the top of a barbecue, you know it feels kind of warm. That heat, without actually touching it, that heat is being conducted to the air, which is in contact with the surface of the outside, and then the hot air expands and rises, and you lose some of that. And naturally you'll need more energy to replace that energy lost, and because you've got a limited amount of power, it's going to take longer than that 5 minutes to go. There's a lot of ways you could describe this energy loss, but you really just need to come back to this diagram here and consider all the things conduction's a big one, because everything where the burners are is in contact with other metal things, and then it'll radiate out and you'll lose heat, because nothing's a perfect insulator of those things. Wherever there are particles, heat will travel. Anyway, that covers it. That's question 2.